Here we have the symmetrizer and the anti-symmetrizer of Sn. They are essentially idempotent, so S squared is proportional to S and A squared is proportional to A. And now let's look which irreducible representations they generate. So first let's multiply this S by any permutation Q. So what's that? That's the sum over all permutations P in Sn, and then we have Qp, but summing for a fixed Q, summing over all Qp is just summing over all elements of Sn again, just in general in a different order. So this is just S. So we know whatever we apply to S, we just get back S. Rearrangement lemma. Now let's apply some permutation Q to any element of the left ideal generated by S. What do the left ideals look like? That's some permutation P times S. So this is in the left ideal generated by S, and now we multiply with some group element Q. Okay, we know it doesn't matter what we multiply S with, we just get back S. But we can also write this as P times S, and now we see that the Q here is represented by this invisible 1 here, so it's really the trivial representation which we get in terms of this primitive idempotent here. Okay, how about the anti-symmetrizer? Proceed in exactly the same way. Let's calculate Q times A. What's that? Sum over all permutations in Sn, sine of the permutation P, now Q times P. So if we had the sign of Qp here instead of the sign of P, this would be the anti-symmetrizer again. So let's just write what we'd like to have. We'd like to have sum over P sine of Qp times Qp, but that's of course not true. The sine of Qp is the sine of Q times the sine of P, and the sines squared are all just 1, so we're missing here a sine of Q. Now it's correct. And now this is the anti-symmetrizer again, so we found the sine of Q times the anti-symmetrizer. And as before, we look at QPA. So QA is in the left ideal generated by A, and then we multiply with Q from the left. Then we get the sine of QP times A by our calculation, the line above. But that's the sine of Q times the sine of P times A. But sine of P times A, that's just P times A. So we have the sine of Q times PA. And now we see that Q here is represented by the sine of Q. So this is the sine itself is another one-dimensional representation.